Hi guys, and welcome to this lecture, which is an introduction to inductors. Now I'm going to start out by saying that this one is going to be pretty full on compared to the other ones. Inductors, even though they're just effectively a coil of wire like this, so in a previous lecture I made this little thing with a screw and some wire around it, that you can call an inductor. Now even though it is just as simple as that, I think it's the hardest one to understand compared to any other lecture that we've done. So hopefully we'll go through it and hopefully we can get things to sink in. Now, so I'll just start out by saying this, and then I'll talk about where we might use these things. But inductors are basically just a coil of wire, just like what we've been looking at in previous lectures. So if you have a look at this thing, I've used this before. In fact, when I was talking about moving this in and out, it induces a voltage. That there can be considered an inductor. This can be considered an inductor. If you have a look down here at the bottom of the screen, we've got a few down there. This one here is an inductor. In fact, that one right there is this one here. And as you can see, if I unravel this thing, it is just a coil of wire. We've also got some smaller ones. Now some of them even look like resistors, like this one here. However, the markings on it are different to a resistor. That one is an inductor, and in there is a really small coil of wire. And we get even smaller ones as well. This one's even got like a resistor color code type thing going on. But again, inside it's wound as an inductor, and they're generally green. So an inductor, coils of wire, where can we use these things? Well, this is a pretty cool little circuit. So I've used these before in different projects, but what this thing does is you put in a low voltage, like let's just get a 1.5 volt battery, and then on the output you can get up to 35 volts, all with the help of this inductor right here. You can actually increase the output voltage using an inductor. And the way that we vary it up to 35 volts is with this potentiometer down here. But we can perhaps look at that a bit later. We use them in radio tuning circuits. So when you're in your car and you're tuning the radio station to something that you want to listen to, an inductor is actually helping you tune into the radio station. We use them to tune into different television channels. We use them in power supply circuits. We use them in what else have I got? I'm sure I'll come up with other applications as we go through. But very handy little device. And there's going to be maybe 2-3 lectures that are going to deal with inductors as we go through. Now, that page was not too bad. This is where we start to get a little bit full on. So this page is going to take some mental brain activity. So what I'm going to go through here is the operation of an inductor. Now, the previous 2 lectures I showed you this one, which was the screw with the wire wrapped around it, and we talked about, well, what would happen if you put a voltage here? Well, when we put a voltage there, we get current flowing through these wires. With current flowing through these wires, we learnt that there's a magnetic field that now builds up around those wires. Then, in another lecture, we got rid of the power supply, and I was just speaking about getting this one, which was hollow. And if I was to connect up a resistor or something to the output of these two, and then I get my magnet and move it in and out, we learned that as the magnet goes in and out, the lines of flux around that magnet cut into the wires, which then induces a voltage into here. As it induces a voltage into there, we now get current flow going through these wires through the external circuit. And just like when we put current flow through this, it generates its own magnetic field. So the current flow through this generates its own magnetic field, and the magnetic field that this generates gives us a north and south polarity that tries to prevent this doing what it's doing. So if this tries to move in, this generates a magnetic field that's going to oppose it to push it out. If this was in there and we try and pull it out, this generates a magnetic field to try and pull it back in. It always wants to do the opposite of whatever is happening. And that's going to be exactly the same for the inductor. Now, using those 2 previous lectures, if we put those 2 together, that's going to form the basis for our inductor. So, let's start off here. In fact, I'll use this as my basis. So we've got this here. This is an inductor. There's no power supply connected. There is no current flowing through this thing. If there's no current flowing through this thing, there is no magnetic field. So hopefully that is starting off very basic, and hopefully that can sink in. Now, as soon as we add a power supply, so I'm going to connect negative to the left, positive to the right. The instant that I do that, current is going to try and flow through the circuit. So when that happens, we get a magnetic field building up around the coils of wire. So let's just trace this one first. In fact, I'll get a different color here. Let's go light blue. So picture this. There's a magnetic field building up around here. And it's getting bigger and bigger and bigger. It doesn't instantly just go from no magnetic field to this big magnetic field just in an instant. It takes time to grow into that magnetic field that it's going to become. Now we can change the size or the magnitude of that magnetic field by changing this power supply. For example, if we make it a 1 volt power supply, the magnetic field might get this big. But if we go to 2 volts, it's going to get this big, and 10 volts would be way bigger than that. So it's going to go to a certain size. Once it gets to that size, it will stop. However, at the moment, we've just connected to the power supply. It's going to really quickly start building up this magnetic field, which, if you notice my hand movements, the magnetic field is actually moving. That's the key thing here. We have a moving magnetic field around this wire here. Now notice what's going to happen. As it's growing bigger and bigger and bigger and bigger, it's actually going to start cutting into this wire right here. Now if we go back to a previous lecture, what happens when we get a magnetic field cutting into the wires? Well, it induces a voltage into the wires, and that's exactly what's happening here. We connect a power supply up. That power supply is going to try and cause current to flow, which causes the magnetic field to get really big, or it starts to move. But as it's moving, there's all these wires next to that magnetic field, so it's cutting into those wires, inducing a voltage into those wires. And then we can go back to everything that I stated about this. Everything's going to be the same. So if we have a moving magnetic field, it cuts into the wires. As it cuts into the wires, we get current flow. We get a voltage induced into those wires, which produces current flow in those wires, which then produces its own magnetic field, which is going to oppose the original magnetic field. So what's happening with this one? It's actually getting a magnetic field that's trying to oppose this one. So it's trying to shut that thing down. So we get it's kind of almost like in a car, if you like. So you know, in a car, you sit in there, you get your seatbelt, you pull it down. If you pull it down really, really quickly, it's got that inertia reel in there, and it stops you. That's the same sort of thing here. We connect a power supply, it's trying to build really quickly, but the very act of the magnetic field trying to build really quickly, it cuts into the wires next to it, and those wires then oppose that build-up of that magnetic field by producing an opposite polarity magnetic field. So essentially what's happening is, the inductor says, no, I don't like this change. Inductors hate change. They want to stay at a state that is never changing. So at the moment we started out with no power supply connected, and the inductor was very happy. There it is, a very happy inductor. Then we come along and connect a power supply. That is where the change comes into it. And the inductor says, hang on a second, I was sitting here all happy, there was no change, now you're trying to give me a power supply, which means you're trying to make current flow through me. I do not want that to happen. So the inductor is going to oppose that. The way that it does that, and I know I'm repeating myself, but I really want to try and ram this home. The way that it can oppose that is by that power supply tries to get current to flow, which makes the magnetic field build. As it builds, it cuts into the wires next to it, which induces a voltage into those wires, which gives us current in the opposite direction to the other current, which produces a magnetic field in the opposite polarity to that magnetic field. So it's trying to shut the whole thing down. However, the power supply eventually wins. This magnetic field just keeps growing bigger and bigger and bigger, but as it actually slows down as that happens. Eventually it gets to the full size, but we'll talk about that quite soon. Okay, so since the magnetic field is moving, because it's getting bigger and bigger and bigger, it actually cuts into the wires next to it. This induces a voltage into these wires, which results in current flow in those wires, which is in the opposite direction. And they make their own magnetic field, which tries to oppose that original one. Now, I've been speaking about we induce this voltage. We have a special name for that whole thing. So over the whole inductor, we're actually getting, there's lots of coils of wire. So not only is that one building up, this one is building up. And it cuts into that one and that one. But not only that, but this one builds up. And it cuts into the ones next to it. If you put all of that together, we get a certain amount of voltage. And this voltage is opposite to the power supply. Because remember, this is trying to oppose that change, and the change is, well, we've connected a power supply. This effect is called back EMF, or back voltage, which means that the inductor is attempting to stop the change that is occurring. Inductors hate change. An inductor is perfectly happy to sit there with no power supply connected. But as soon as you try and change this by applying a power supply, it will do all it can to stop this. Eventually the power supply wins this battle and the magnetic field around the inductor will reach its maximum strength. At this point though, the magnetic field stops moving and the inductor is happy again. The inductor is only not happy when something is changing, because if something is changing, it means the magnetic field is building. It's either getting bigger or it's getting smaller, depending on if we've connected a power supply or disconnected a power supply. So eventually what's going to happen is these magnetic fields are built up to their full strength and now they've stopped moving. And remember, that happens all over the whole thing. In fact, we can draw it like this. So remember how we drew our bar magnet? Because they do in fact all group together. So eventually we get a magnetic field and it's built to whatever that power supply voltage would allow it to build to, and now it stops moving. And the inductor says, ah, good, we've stopped moving, I'm happy again. Because if it's not moving anymore, we're not cutting any lines of flux through any wires, therefore we're not inducing a voltage into them to try and oppose what's going on. So the inductor is all good. However, the inductor is not going to be happy if you come along and... okay, just let me move that. I'm going to try and... oh, this is terrible. What I'm trying to do is get rid of the power supply. Oh boy. Okay, here we go. There we go. Okay, so we've gotten rid of the power supply. The inductor says, hang on, I don't want this change. I want to keep my magnetic field stationary as it was. But hopefully you can see, if we've got no power supply there anymore, we no longer have that current to hold that magnetic field in place. So what do you think is going to happen to that magnetic field if we can't hold it there anymore? Well, it's going to have to start to collapse. And the inductor does not want that to happen. The inductor wants it to stay stationary, whatever that stationary point is. So now power supply is gone. We no longer have that current to keep the magnetic field there, so the magnetic field collapses. As it collapses, it's kind of like us bringing the magnet out here. It's actually moving again. As the field moves, as in it's getting smaller and smaller and smaller, it's again cutting through the wires. As it cuts through the wires, it induces a voltage into those wires, which then gives us current flow in those wires, which then gives us an opposing magnetic field. It's trying to make that magnetic field go back to where it was. So the key thing to remember with inductors is they hate change. Anytime you want to change, increase or decrease current, they're going to go, no, I don't want that to happen. I'm going to oppose that. But eventually, because there's losses within an inductor, it cannot just keep that magnetic field there. It will eventually collapse to nothing, but it takes time to do that. So let's go to a page that's a little bit simpler. Inductors are actually measured in henries, which is named after Joseph Henry, and are given the symbol or the letter L. So just to recap on a couple of things, you've got resistors, which are given the letter R, and they're measured in ohms. Capacitors are given the capital letter C, they're measured in farads, and inductors are given the capital letter L, but they're measured in henries. So that's how that all ties in. So if you're looking at a circuit and there's an L there, you know, oh, that's an inductor. If there's an R there, you know, oh, that's a resistor. This is the circuit symbol. Oops, that's not what I want. That's a circuit symbol right there. Just a few bumps. And again, I've said this many times, but the key concept with inductors is that they hate change. If you try and increase current through them, they will do whatever they can to decrease it back to where it was. Increase, they'll try and decrease. If you try and decrease it, they'll try and increase it. They're always going to do the opposite of whatever you're trying to do. Now, we'll have a look at this circuit, and then that'll be the end for this particular lecture. But then the next lecture is going to go into inductive, resistive time constants, just like we did for capacitors, but now we're using inductors. So we'll have a look at that if you remember the universal time constant chart where we had these things. The next lecture we'll be looking into that and doing some calculations. So what we want to do is we first want to charge this thing up. At the moment, nothing's connected there, so there's no current flow, there's no magnetic field, there's nothing. And the inductor is perfectly happy with that. If we were to connect that up to there, and it doesn't matter what this is, I'll just put a value there, 10 volts. We're now going to get this current flow going up through there like that. So that's going to cause this to get a polarity of negative with respect to positive. And it's going to cause a magnetic field to start to build up. Now, when we first connect that switch, the magnetic field moves really, really quickly because it's trying to get to this big magnetic field like this, and it tries to do that really quickly, which means it's moving really fast. If it's moving really fast, it's kind of like me really moving this into there really, really quick. The faster that it moves, the more of a voltage gets induced into the wires next to it. So initially, when we first turn this on, this is going to have the full 10 volts, simply because the magnetic field is moving so quick that it's cutting into those wires so fast that induces a huge voltage, which is 10 volts. Therefore, we get 0 volts across the resistor. That's when we first turn it on, and we'll deal with this more when we get to the next lecture as well. Now what happens is, over time, kind of like if you were running a race, you start off really quick, but then you keep slowing down. The field moves really quick, but then it slows down how fast it's moving. As it slows down, we're not cutting into those wires as quickly, so the voltage actually that we induce drops. So it goes to 9 volts, and this goes to 1 volt. And then we keep going, and this goes to 8 volts, and this goes to 2 volts. It actually does the exact opposite of a capacitor. So what's happening is the magnetic field is building, and it's building, and it's building, and it slows down. So it's building really quick, but then it slows down, and eventually, and we'll get into this later, but 5 time constants later, the magnetic field is built to its full size. When it gets to its full size, it stops moving, and the inductor is now happy. When that happens, because it's not moving anymore, it's not cutting any lines of flux with the wires, so it's not inducing a voltage anymore. So we get 0 volts there and 10 volts there. Nothing else is changing, the inductor is happy. But what happens when we try and discharge this thing? Well, let me just get rid of that. When we discharge it, we bring this down to there. In fact, I do need to get rid of that, don't I? We bring that down to there. Now the inductor is not happy with this. It doesn't want change. It wants to keep current going exactly as it was. It wants its magnetic field to stay where it was. So what's going to happen is there's no power supply to keep that magnetic field there. So the magnetic field has to collapse. So instead of moving outwards, it's moving inwards. Now that it's moving inwards, it's kind of like me, instead of moving this in, it's moving out like this. So we're just moving the magnetic field in the opposite direction. So what's that going to do? Well, instead of having negative positive like that, it's now going to swap, because the negative positive was produced by moving the magnetic field out. We're now moving in. So we're going to get a polarity of negative positive. So it is going to, this is now acting as the power supply. It's now going to have current going in this direction like that. Notice how it's trying to keep current going in the same direction as it was going before. Previously, current was going up through the inductor like this. And that's exactly what the inductor is trying to do. The field collapses, it induces a voltage into itself with the opposite polarity, because it's not, instead of moving out, it's moving in, so the polarity has swapped. But notice how it's trying to keep current going in the same direction. So eventually, it's not going to be able to keep that voltage there. Eventually it'll lose out. It's got losses within the inductor, and we go back to no magnetic field whatsoever. So now this lecture, I know, is a really hard one to grasp. Perhaps you should watch it more than once. But when we get to the next lecture, we're going to delve deeper into this one. We're going to look at the universal time constant chart. We're going to talk about the 5 time constants and how long it takes to charge up to its full magnetic field and so forth, and what happens when we discharge it. So hopefully that'll be a little bit of fun. Okay, well, some questions coming up, so see how you go with them, and thanks for watching.